くりレ夢ムです。
ゆっくりマリサだぜ。
Hi, Raimo. Hi, Marissa. Hey guys. The last number. The impossible mystery of where counting actually ends.
ゆっくりしていってね。
Section 1. Hook. Here's a question that sounds simple. So simple, in fact, that most people dismiss it in about 2 seconds. Is the last natural number even or odd? 1, 2, 3, 4, 5. You've been counting since you were 3 years old. You know how numbers work. Even numbers end in 0, 2, 4, 6, 8. Odd numbers end in 1, 3, 5, 7, 9. They alternate, back and forth, forever. So which one comes last? Go ahead, think about it. If you just said, there is no last number, you're right. And that's exactly where the mystery begins. Because the moment you accept that numbers never end, that there is no final number, no last digit, no ultimate count, you've just opened a door into one of the deepest, strangest, most fiercely debated territories in all of human thought. A place where mathematicians have disagreed for centuries. Where the answer to a simple question turns out to implode everything you thought you understood about numbers, infinity, and the structure of reality itself. What happens at the end of the number line? And what does it mean that we can't get there, but mathematicians have tried anyway? Section 2. The story begins. Let's start with something everyone agrees on. Natural numbers are the counting numbers. 1, 2, 3, 4, going upward forever. No fractions, no negatives, just the clean, whole numbers you'd use to count sheep or dollars or stars. The ancient Greeks thought about them. So did Indian mathematicians over 1,000 years ago. And for most of history, the question of where they end didn't really come up because it was assumed, intuitively, that they just kept going and you didn't need to worry about the end point. Then, in the late 1800s, a German mathematician named George Cantor decided to take infinity seriously. Not as a vague concept, not as a metaphor for a really big number, as a mathematical object that could be studied, measured, and compared. And what he found, what he proved, rigorously, using logic that other mathematicians eventually had to accept even when they hated it, turned the mathematical world upside down. Cantor showed that infinity was not just one thing. There were different sizes of infinity. Some infinities were bigger than others. And suddenly, the question of what happens at the end of the natural numbers wasn't a silly question anymore. It was the most important question in mathematics. Section 3. The evidence. To understand the mystery, we need to understand what mathematicians actually mean when they talk about the natural numbers and their infinity. Because the evidence, once you see it, is genuinely strange. Exhibit 1. Infinity is not a number, except when it is. Here's the first thing that breaks most people's intuition. In ordinary mathematics, the kind you learned in school, infinity is not a number. It's a direction, a destination you move toward but never reach. You can say as x approaches infinity, but you can't say x equals infinity and do normal arithmetic with it. 1 plus infinity? Undefined. Infinity divided by 2? Doesn't make conventional sense. So when we ask, is the last natural number even or odd? In standard mathematics, the answer is simply, there is no last natural number. The question assumes an endpoint that doesn't exist. But here's where it gets interesting. Because mathematicians, being mathematicians, decided that it doesn't exist was not a satisfying place to stop. So they built systems where it does exist. They invented what are called transfinite numbers, a framework where infinity can be treated as an actual mathematical object, with its own arithmetic, its own properties, and its own strange rules. And in that framework, the question of whether infinity is even or odd suddenly becomes not just answerable, but fascinating. Exhibit 2. Cantor's Infinite Hotel. Before we get to the answer, we need to understand Cantor's most famous thought experiment. because it reveals something about infinity that still feels wrong no matter how many times you encounter it. Imagine a hotel with infinitely many rooms. Every room is occupied. A new guest shows up. Is there room? In a normal hotel, no. Full means full. In Cantor's infinite hotel, yes. Easily. You just move the guest in room 1 to room 2, the guest in room 2 to room 3, and so on down the infinite line. Now room 1 is empty. The new guest moves in. The hotel was full. You added a guest. It's still full. This is not a trick. This is what infinity actually does. It means that the set of natural numbers, 1, 2, 3, 4, has the same size as the set of even numbers alone, 2, 4, 6, 8, even though the even numbers are only half of all natural numbers. Infinity divided by 2 is still infinity, the same size of infinity. Your brain resists this. That's normal. The resistance is the evidence that something genuinely strange is happening. Here's something that may reorganize how you think about numbers entirely. Cantor didn't just show that there were different sizes of infinity. He showed that some infinities are so large that you can never list all their members, even with infinite time. The infinity of natural numbers can, in principle, be listed 1, 2, 3, 4, and so on. It would take forever, but there's a method, a sequence. The infinity of real numbers. Numbers that include every decimal, every irrational number like pi, every point between 0 and 1, cannot be listed. Cantor proved this with a technique called the diagonal argument. No matter how you arrange real numbers in a list, there is always a real number that isn't on it. Some infinities are literally bigger than other infinities. And the infinity of natural numbers, our counting numbers, is, in this framework, one of the smaller infinities. There are infinities that dwarf it, completely, incomprehensibly. Exhibit 3, ordinal numbers and the omega. Now we can get to the real heart of the mystery. In the late 1800s, Cantor introduced a concept called ordinal numbers. These are numbers that describe position and order, first, second, third, extended beyond the finite into the infinite. The natural numbers go 1, 2, 3, 4, 5, and they never stop. But if you ask, what comes after all of them? Cantor had an answer. He called it omega, not because the question doesn't apply, but because evenness and oddness, as mathematicians define them, apply to natural numbers, and omega is past natural numbers. It exists in a different mathematical territory where the standard definitions of even and odd don't automatically transfer. You've reached a place on the number line where the rules of arithmetic you've known your whole life simply stop applying. But wait, because this is where it gets genuinely controversial. Not everyone accepts Cantor's framework. When Cantor first published his work on transfinite numbers in the 1870s and 1880s, the mathematical establishment didn't just push back. Some of them were openly hostile. Henri Poincaré, one of the greatest mathematicians of his era, called Cantor's work a disease that mathematics needed to recover from. Leopold Kronecker, another major mathematician of the time and one of Cantor's former mentors, attacked his work publicly and persistently. He believed that infinity should never be treated as a completed object, only as a process that continues without end. Kronecker once reportedly said, "God made the integers. All the rest is the work of man." In other words, natural numbers are real. Everything Cantor was building beyond them was human invention. Useful maybe, but not truth. That debate, between those who accept completed infinities and those who reject them, was never fully resolved. It just got quieter as Cantor's framework became dominant. But the dissenters never fully disappeared, and their objections still echo in modern mathematics, in ways we'll come back to. Exhibit 4. What happens when you try to add 1 to infinity? Let's stay in Cantor's framework for a moment and push it further. Because the arithmetic of transfinite ordinals is one of the strangest things in all of mathematics. Omega plus 1 exists. It is a number, It comes after omega. Omega plus 2 exists, and omega plus 3, and so on. Then comes omega times 2, then omega squared, then omega to the power of omega, then epsilon naught, a number so large it takes an infinite tower of exponentials just to describe it. And all of it, is still countable, still in the same basic size of infinity as the natural numbers. There are infinitely many transfinite ordinals before you even reach the first uncountable infinity. And none of them, not omega plus 1, not omega squared, answers the original question. Because none of them are the last natural number. They're all beyond the natural numbers. The natural numbers don't have a last member, but the space beyond them is incomprehensibly vast. That's section 4, the theories. So we've established what the mainstream mathematical framework says. But the question, is the last natural number even or odd, isn't just a math question. It's a question about the nature of infinity itself. And there are genuinely different schools of thought, each with serious intellectual pedigrees, that answer it differently. Theory 1. The question is meaningless. There is no last number. This is the standard position in mainstream mathematics, and it has been since Euclid proved that primes are infinite over 2,000 years ago. The argument is simple. Natural numbers are defined as an infinite sequence. Asking for the last one is like asking for the largest fraction. The concept is incoherent. There is no answer because the question assumes something that doesn't exist. Under this view, the even or odd question is not mysterious. It's just malformed. Like asking, what's north of the North Pole? The answer isn't north or south. The question doesn't work. The strength of this theory, it's clean. It requires no exotic machinery. The weakness, it leaves the deeper questions about infinity completely unaddressed, and those questions don't go away just because you call them malformed. Theory 2. Infinity is even by definition. Here's where it gets interesting. In some mathematical frameworks, particularly in modular arithmetic and certain number theory contexts, there are ways to define the parity, evenness, or oddness of infinite quantities. The most famous example involves a technique called regularization, a method of assigning finite values to infinite series that would otherwise diverge. Using this approach, mathematicians have argued that the sum of all natural numbers, 1 plus 2 plus 3 plus 4, going on forever, equals negative 1/12. Yes, negative 1/12. That is a real result used in theoretical physics, particularly in string theory. And some extensions of parity to infinite ordinals define omega as even, because it is the limit of even indexed terms in certain sequences. The strength of this theory, it's internally consistent and mathematically productive. The weakness, it requires accepting definitions of even that are very different from the ordinary ones, and the results, while useful, feel more like convention than discovery. Theory 3. Infinity is odd because the pattern demands it. A different school of thought looks at the alternating pattern of natural numbers. Odd, even, repeating perfectly, and asks, if the pattern is perfect and unbroken, doesn't that tell us something about the limit? Some mathematicians who work with non-standard analysis, a rigorous framework for doing calculus with actual infinitely large and infinitely small numbers, developed by Abraham Robinson in the 1960s, work with infinite integers that can be even or odd just like finite ones. In non-standard analysis, there exist numbers larger than any natural number that are still, rigorously, either even or odd. You can have an infinite integer that is even. You can have one that is odd. Under this framework, the question, is the last natural number even or odd, doesn't get one answer. It gets both. Because in the non-standard universe, there are infinite natural numbers of both types. It depends which one you mean. The strength, it treats infinity with the same rigor as finite numbers without losing the even-odd structure. The weakness, It requires accepting a radically expanded number system that most mathematicians don't use in daily practice. Theory 4. The question reveals something about the limits of logic itself. The fourth theory steps back from the mathematics entirely and looks at what the question is doing. Philosophers of mathematics, particularly those working in the traditions of intuitionism and constructivism, argue that the question, is the last natural number even or odd, is not just unanswerable. It is revealing. It reveals that human mathematical intuition, built up by counting finite collections of real objects, breaks down when applied to the infinite, and that the frameworks we've built to handle infinity, Cantor's transfinite numbers, non-standard analysis, regularization, are human constructions, useful tools, not windows into a pre-existing truth. Under this view, infinity is not discovered. It's invented. And the even or odd question doesn't have an answer in nature, only in whichever system of rules you've agreed to follow. This is the most philosophically radical position, and for many people, the most uncomfortable, because it suggests that some of the deepest questions in mathematics don't have right answers. They just have choices. Section 5. The most likely answer. So what does the evidence actually support? Here's my honest assessment. In standard mathematics, the framework used by the vast majority of mathematicians, taught in universities, and used in engineering and physics, there is no last natural number. The question is not answerable because the premise is false. Natural numbers are infinite. They don't end. But, and this is important, that answer is only satisfying if you stop there. Because the moment you push past it and ask what does infinity actually mean, and what rules does it follow, you're in genuinely contested territory. The different frameworks, transfinite ordinals, non-standard analysis, intuitionistic mathematics, give genuinely different answers. And they're all logically consistent. The most honest thing I can tell you is this. The even or odd question is not a trick question with a hidden obvious answer. It is a depth gauge, a tool for measuring how far you've thought about what numbers actually are. For most of history, humans used numbers to count things, finite things. In that world, even and odd are clear, simple, permanent. The moment you try to count something that never ends, to apply the rules of finite arithmetic to infinite quantities, you discover that the rules were never fundamental. They were useful, locally, within limits. Beyond those limits, mathematics doesn't break, but it changes. And what it changes into is strange and beautiful and unresolved in ways that should make all of us a little more humble about how well we understand something as basic as numbers. Numbers feel more certain than almost anything in human experience, more reliable than memory, more stable than relationships, more permanent than stone. And then you follow the numbers far enough, past 1 billion, past 1 trillion, past any number you can name, and you find that the bedrock doesn't continue forever. It ends. Or rather, it doesn't end, which is somehow stranger. There is no last natural number, but there is something on the other side of all of them. A place in the mathematical landscape that Cantor named and explored and proved exists at the cost of his sanity. He suffered a mental breakdown. He spent time in a sanitarium. He died in one. Whether that was caused by his mathematical work or by the professional cruelty of colleagues who called his life's work a disease, we'll never fully know. But there is something poignant about a man who spent his life staring at the place where counting ends, trying to describe what he saw there. The answer he came back with, that there are infinitely many infinities stacked beyond each other into incomprehensible distance, is now standard mathematics. And the question he was trying to answer, what is the nature of the infinite, is still open, not because we haven't thought hard enough, but because the infinite, by definition, is larger than any answer we can fully fit inside our heads. So here's the question I'll leave you with. It's the one that Cantor's work ultimately forces you to face. We live in a universe that appears to be finite in some ways, a finite number of particles, a finite amount of time since the Big Bang, and infinite in others, or possibly infinite in others. If the natural numbers go on forever, but forever doesn't have a last step, does that mean infinity exists in reality, or only in our minds? And if it only exists in our minds, what does it mean that our minds can contain something the universe might not? Do you think infinity is real, or just a useful idea? Tell us in the comments. We read every one. Subscribe for more investigations into the hidden mysteries at the edge of human knowledge.